to session number 2 of the on-demand computer science grind. Today we're going to be covering chapter 2 in the notes, and that is data types and number systems. It's a very small chapter, but it's one that's very common, comes up very often, especially in the short questions section. So we'll get straight in. I'm going to drop this in on page 10 of the notes. So we're going to get started first of all with just the short part of the chapter on the different types of data that we have in computer science. So what you need to know here is you need to be able to look at a piece of information you could be given and then match that to the type of data that it is. So the first type of data that we have is integers, or int, int, as I represented in code. And integers, as you might know from maths, this is your positive and negative whole numbers. So that's 0, 13, minus 21. They're all integers, right? Something like 9.7. That is not an integer because it's not a whole number. Okay? So that's your integers. What 9.7 is what's called a float number. Float is the computer science term for a decimal number. So this would be the likes of 9.7 minus 0.39, 100.01. All examples of float numbers. Key distinction then between these two, right? So 13 would be an integer. 13 as a float would be written as 13.0. So if you ask a program to print the number 13 as a float number, it will print 13.0 because there has to be a decimal in there somewhere. Okay. Next one, I have to draw on the jumper. Anyway, so the next one then is a character, or CHAR. And this is just any single character by itself. So the letter A, the number 9, I think the two examples I have there. Yeah, A9, etc. Anything that's on its own is a character. Next up then for letters, or sentences even, would be strings, or STRs. So a string is anything that's in quotation marks. So I love to code would be an example of a string. And strings you can represent either using, I suppose, inverted commas, or you can also use quotation marks. Either of those two is fine once you're consistent, right? You can't have a quotation mark followed by an inverted comma, because then that will be recognized as a string. Okay? Next up then we have dates. So a date is literally just as it is in real life, it's a date. So if we go with today's date, which is, when is today's date? I think it's the 9th of the 12th, 2024. Date. No further explanations needed there. Next up then we have an array. I'll do these over here. So an array is something that is composed of multiple values, so a list essentially. So that could be, what's the example that I have there? Yeah, so like an example of a list, right, would be dog, cat, mouse. Sorry. So you see each of these individually is a string in its own right, but when you put multiple of them together, you get an array, which in this case is a list. Key thing here is they have to be separated by commas. That's how you recognize an array, and in this case the square brackets would define this as a list. And the last one then is Boolean data types, or Bool. So a Boolean variable is one that can only have two possible values, right? True or false. Can only be yes or no, true or false. It's a Boolean variable. So in fact, those of you who go on to study maybe physics or computer science at college, you'll learn about Boolean algebra. Boolean algebra was invented by an Irishman called George Boole. So we have a lot of computer science to thank for that man. So that is pretty much all your data types summed up. Actually, sorry, I'm forgetting, I suppose, a little notice at the end. You could be asked about a compound data type. So a compound data type is just a piece of data that has multiple different types of data within it. So, for example, right, you could have a list, and this list here has all strings in it. You could have a list with strings and integers, floats, different types of data within that. That would be a compound data type. Okay? So, yeah, lists, tuples, and dictionaries. That's pretty much all there is to that. We'll do a quick exam question just to kind of show you how it comes up. So you will actually, sorry, I meant to say you will need access to exam papers to some extent for this class. So you want to pause the video and then go and get one, either I don't know, a physical copy that you might have from school, or if not, I will provide all the exam papers in the Google Classroom to give access to these videos to as well. So the one I'm going to do just very, very quickly is question 1 from the 2023 paper. So I think I want to just do it down here. So 2023, question 1. So, question 1 just says, enter the appropriate data type in column B to match the values in column A. So, I'll write out the data, or the actual data itself first. So first of all, we have Kira, and we have 2, 5, 5, and we have 3, 1, 2, 3, 4, 5, 6, 7, and 1.5, 7. 1.2, 0.9, and 1.3. False. And then finally the number minus 99.99. So now we need to correctly correctly identify the type of data that each of these is. Okay? So the name Kira, if you want to store the name Kira in a variable in a piece of code, you would have to store it as a string where you put your inverted commas there, and this would be a string. Next up then, 255 is obviously just going to be an integer. Now, 083, 1, 2, 3, 4, 5, 6 is obviously a phone number, somebody's phone number. Now, your first instinct might be to say, okay, it's a number, so we can store it as an integer. But we can't, because looking at it directly as it's printed, we see we have a dash here. So if we want to print this number, or store it even exactly as it is here, it will have to be in a string. Okay. Next up then we have a collection of numbers with decimals. So each of these is going to be a float number, but it's a collection of float numbers separated by commas. So it's an array. Or we can be specific in this case, we can say it's a list. Either or is fine. Okay, false is, of course, going to be a Boolean variable, because that can only be true or false. So bool. And then finally, minus 99.99. It has a decimal, so it must be a float. And that was that question done. Very kind of, I think, a nice question to start off that year's exam. In terms of marks then, I'm pretty sure it was just, let me just double check. Yeah, so that question was worth 6 marks, 1 correct mark for each when you identified. Okay. So, that is data types pretty much covered. So now we're going to move on to the more important part of this chapter, which is number systems. We're going to focus on the most important number system to start with, and that is, of course, binary. So we're still on page 10 of the notes here, just a bit further down. So binary, as hopefully you may know at this stage, is the number system that computers use to store all their information. And binary is made up of ones and zeros. So binary is described, it's what's called a base 2 system. What does that mean? So the numbers that you and I are familiar with, right, are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Right? There are basic numbers, and then every number that comes after 9 is made up of some combination of 2 or more of these numbers, right? So, 0 to 9, 10 numbers, right? So, our number system is what's referred to as a base 10 system. A base 10 system. Right? Because we have 10 basic numbers. Like I just said, binary is a base 2 system, meaning it stores all its information with just 2 numbers, which, as we know, is 0 and 1. Okay, so binary, base 2 system. So why? Why go to the bother of doing this, creating a new number system when there was a perfectly good one in existence? The reason for that is because of the inclusion of a component in computers called transistors. Now, transistors we'll come back to in a bit more detail once we start talking about computer systems in later sessions. But essentially, what a transistor is it's a switch. So when an electric signal goes through a transistor then sends a signal either on or off, right? So this is your signal, right? You might get an on, and then an off, and then an on, and then an off, and then an on, and then an off, and so on, right? That will continue for ages. So this is the signal you get from your transistor, right? Now, electronically, what this represents is the transistor sending a signal of 0 volts and it's sending a signal of 5 volts. Okay? So, you see here, we have 2 states, right? 0 volts or 5 volts on and off, and also, would you believe, 0 and 1. So that's why we use a 2-number system, is because of the transistors and how they operate, right? And that description that I was given there is also detailed in the notes. That is something that has been asked and that can be asked, is why do we use the binary system? So what is the benefit of using this binary system? It means that because you're only dealing with, right, there's two states, on and off, there's no in between, right? There's no maybe, it's either on or off, right? It's a 1 or a 0, it can't be anything else. So what that means is binary is a very, very reliable system. It's very reliable for communication. It's very hard for mistakes to be made when using the binary system. And that's the benefit of using it, and it's why it is used. Another reason why it is used. So, moving on then to how computers actually store information. So computers store information, as we know, using binary, right? So if you were to look at a piece of information, right, say your name in text, right, and you looked at that as binary, it would look something, it'll be a combination of ones and zeros. And that will go on and on for ages, right, depending on how long the piece of information is. So each of these pieces of binary, right, each of these either ones or zeros, right? So this one, for example, right, we would call that a digit, right, in our number system. So this is a binary digit, or, as you may have heard, a bit. So computers store information in bits, and the number of bits that you have depends, the amount of information you can store depends on how many bits you have. And we can work that out mathematically, right? And I say maths, don't get scared, this maths is very simple. So, how many pieces of information? So one bit, right, can be either one of two states. It can be a 0 or a 1. So we have two different states. Okay? So if we have one bit, right? So 2 to the power of 1. That is up to two pieces of sorry, I'm going to rephrase that. One bit, two possible combinations, or two possible values, 0 or 1. Okay? If we increase the number of bits that we have, so let's say we now have 2 bits, so that'll be 2 to the power of 2. That is 4 possible values that we can have. Okay? If we increase it again, 2 to the 3, that would be 8 possible values. 2 to the 4, you can see where this is going. This will be 16. When we keep going, 2 to the 5, 32. 2 to the 6, 64. 2 to the 7, 128. For the even, so that's as high as we need to go. This obviously extends much, much further, but for computer science, in this context, we'll deal with 8 bits. Actually, I'm forgetting a bit here at the end side. We got 2 to the 0. If you know from your rules of indices, anything to the power of 0 is 1. Okay? So, that's how the number of bits that we have changes with the amount of information that we can store. So, you'll notice right, that the pattern is 2 to the power of x, right? So, what do we now do with these numbers, right? So you'll see, right, these numbers are 124 up to 128, right? These are going to be essential now for the rest of the class. Because what we got from these numbers was we got a standard way to store information, right? So computers were being obviously developed all around the world, and they needed a standard way for communication to be made and for data to be programmed so that communication could be done easily and it could be done worldwide. So, a group of people came together and formed ASCII. ASCII, the American Standards Code for Information Interchange. And essentially what they did was they came up with this big database that mapped all the numbers and all the letters and gave them a special code. So, for example, the ASCII code for capital A is the number 65. So, when a computer receives a binary input and decodes that as the number 65, it then knows to print the number capital A. And that will happen no matter where the computer is all around the world. They all do the very same, well, they used to. We've moved on from ASCII now because we have so many letters, characters, emojis now. We'll get onto that in a few minutes. But for now, we look at ASCII. So the code for A is 65. So the computer sees the number 65, it goes, okay, I need to print the letter A. So, for the purposes of the exam, what you need to be able to do is show how the letter A would be printed in binary given that its ASCII code is 65. So how do you do that? So, as I said, for the leaving cert, we deal with 8 bits. So you write out those 8-bit numbers that I just wrote out a few minutes ago. Right, so they were 1, 2, 4, 8, 16, 32, 64, and 128. So we sorry. Small mistake I made there. Do them from highest to lowest. Oh, because that'll make it a lot easier. So 128, 64, 32, 16, 8, 4, 2, and 1. Haven't left any there, shall I? No. So, what you do now is starting from the left, so 128, you ask, does 128 go into 65? The answer obviously is no, right? So we put in a 0, okay? Does 64 go into 65? Of course it does. So we put down a 1. Now we do 65 minus 64 is 1. So now we ask, does 32 go into 1? Obviously doesn't. So it's going to be a 0. Does 16 go into 1? It doesn't. Neither does 8 or 4 or 2. Does 1 go into 1? See, it does. So we put down our 1. And then 1 minus 1 is, of course, 0. So, the letter A, or the capital letter in binary, is 0, 1, 0, 0, 0, 0, 0, 1. Okay? It's as simple as that. So, if we do this through example, right? So if you now go to the top of page 11 in the notes, right? It says, using 8-bit ASCII, which is what we're using here, represent your name in binary notation. So, what I would encourage you to do, first of all anyway, is pause the video now, look up the ASCII code database and find the codes that correspond to the letters in your name. So pause the video now and go do that at least. Okay, so hopefully now that you've done that and you're back, right? I suppose if you haven't done that, you can just do my name. So we'll do that. So, my name is T. I should probably space that out a bit more. T-A-D-H-G. So, I've looked at mine already. So, the code for capital T is 84. Lowercase a is 97. D is 100. H is 104. And G is 103. So, all you have to do now is basically convert all 4 of those numbers, all 5 of those numbers even, into binary and then just put it together as one long string. So what I might do for this is, the handy thing is probably to do a table. So if I do that, so 128, 64, 32, 16, 8, 4, 2, and 1. Do. And then down here we have 84, 97, space that more of 100, 104, and 103. So, let's start. So, does 128 go into 84? No, it does not. Key thing to remember now is you're dividing these numbers into these numbers, not these numbers into this number. Right? That's the most common mistake I made. Because obviously if you were doing it this way, you would get an answer of 1 and your binary number would be very wrong. So 128 does not go into 84. Does 64 go into 84? Yes, it does. So we put down a 1. So then 84 minus 64 is going to be 20. So does 32 go into 20? It does not. Does 16 go into 20? It does. So 20 minus 16 is 4. Does 8 go into 4? No, it does not. Does 4 go into 4? Yes, it does. So then 4 minus 4 is 0. So then we can just fill the last 2 digits then as zeros. So there's the first line done. Now it's a matter of just repeating that. So 128 into 97 does not go. 64 into 97 does indeed go. So 97 minus 64 is that is 3, and that is 33. So 32 into 33 does go. So minus 32 leaves us with 1. So we can just then go over to 1, fill it in as a 1, and we can just fill in the rest of these as zeros. So 100 now. 128 into 100 does not go. 64 into 100 does go. So that'd be a 1. 100 minus 64 is 36. So 32 into 36 does go. So 36 minus 32 is 4. 16 into 4? Nope. 8 into 4? Nope. 4 into 4? Yes. And 4 minus 4 is 0. So 0 and 0. Okay. 128 into 104 doesn't go. 64 into 104 does go. That leaves us with 40. So 32 into 40? Yes. This is with 8. 16 into 8? Nope. 8 into 8? Yes. 8 minus 8, 0. So 0, 0, 0. And finally 103. So 128 into 103? Nope. 64 into 103? You betcha. So 32 into 39? Yes, indeed. So 39 minus 32 is 7. 16 into 7? Nope. 0. 8 into 7? Yes. So 1. No, sorry, I was thinking 7 into 8. 4 into 7? Yes. So 7 minus 4, going to give us 3. We'll put 1 here. 2 into 3? Yes. Here minus 2 is 1. 1 into 1. That's very quicker. We'll do that again. 1 into 1? Yes. And then 1 minus 1 is 0. So, from that, my name in binary, TADHG, will be 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 0, 1. 1, 1, 0, 0, 1. 1, 1, 0, 0, 1. 0, 0. Am I missing a number? What? Oh, I forgot a 0 at the start. That's fine. Then 0, 1, 1, 0, 1, 0, 0, 0. That's become very crooked. 0, 1, 1, 0, 0, 1, 1, 1. So that is my name in binary. Hopefully you've done the same with your name. If you've just done mine, fine. At least if you understand it, then that's all that matters. So that is going from decimal numbers to binary numbers. Okay? So, and that is ASCII. So, we said right at the start, right, ASCII was encoded in 8 bits, right? It's 2 to the 0 up to 2 to the 7 is 8 bits. And that was enough to store capital letters, lowercase letters, numbers, symbols, that kind of stuff, right? However, there is more than just our letters and numbers in the world alphabets. There's Chinese characters, Japanese characters, Arabic characters, all these kinds of things. So ASCII was kind of starting to show its limitation, right? It was running out of space. So we had to come up with a new system for storing even more information. And that was where Unicode comes in. So, page 11, 2.4, Unicode. So, Unicode, or the Unicode standard, again, like ASCII, it's a standard for storing information and standardizing it so it's done the same worldwide. So the principle is the same. It's just using a different method so that more information can be stored. So, Unicode is encoded in the hexadecimal system. So, hexadecimal, there's 15 different values, right? There's 0 to 9, or sorry, yeah, 15 different values. So 0 to 9, and then 10 through 15 is A, B, C, D, E, and F, right? So, for example, hexadecimal number could be C3. And there can be much more information stored in that than there would be in an ASCII encoding, right? So the advantage of Unicode is that you can store a large amount of information in a small amount of bits. Okay? So if you're asked at the bottom of the page, if you're asked to compare Unicode versus ASCII, so the The benefit of both is you can store information in a standard way, as I've said, and so worldwide communication is easily done. So the limitation of ASCII point 3 is it's only capable of storing 128 characters, and there's much more than 120 characters in existence, as we've said. Unicode, however, is 32 bits, so twice as long, and that is up to 4 billion characters. So it's very likely to ever run out of space, not anytime soon anyway. So now we move on to page 12, converting binary to decimal. And we'll come back to Unicode in a second when we start dealing with hexadecimal. So, converting binary to decimal, so going the opposite way to what we just did. It's very straightforward. So, we'll do the example there, right? So that is express the binary number 1 0 0. Okay, so 1 0 0 1 1 0 0 1 as a decimal number. So for this, all you do is write. So first of all, write the ASCII numbers, we'll call them, above each of these, right? So 128, 64, 32, 16, 8, 4, 2, and 1. Then all you do is look at what numbers have ones and add them all up. So in this case, this number will be 128 plus 16 plus 8 plus 1. Quick thing to note as well is you need to be able to do this in your head. In the exam, you will not have a calculator for any of these conversions or any kind of maths there is in computer science. It all has to be done here. So 128 plus 16 is 144, plus 8 is 152, plus 1 is 153. It's okay using a calculator for now, as you're doing these or you're studying, but make sure come the exam you can do. Even though it's simple, I know simple maths can kind of slip as your maths gets more and more advanced. It can be hard to forget the basics. It can be easier to forget the basics. So make sure you're able to do that before you go into the exam in your head. So, converting the other way, very, very straightforward. So, converting decimal to binary, we've covered already. I'm just going to do a quick check of how I am for time. Okay. So converting decimal to binary is the exact same as the doing the ASCII to binary. We're just using different numbers. Okay. So we'll do a quick example of that anyway, but it should hopefully be self-explanatory. So convert 141 to binary. So 141. So again, write out your numbers. So 128, 64. 32, 16, 8, 4, 2, and 1. Same process again. 128 into 141. Yes. That leaves you with 13. 64 into 13. Nope. 32. Nope. 16. Nope. 8? Yes, sir. 13 minus 8 is 5. 4 into 5? Yes. Leaves us with 1. 2 into 1? Obviously doesn't go. And 1 goes into 1. 1 minus 1 is 0. So that's decimal to binary. Pretty straightforward, I think. What we'll move on to now is the interesting stuff. Top of the next page, page 13, converting binary to hexadecimal. So, the example there, right? So convert the binary number 11001001 to hexadecimal. So 11001001. So for conversion to hexadecimal, the first thing we're going to do is kind of know there, but split up, in this case, the 8-bit number into two 4-bit numbers. So, if we do that first, so 11001001. So now what we're going to do is we're going to write out some of our numbers again, right? But instead of going from 128 down to 1, we're just going to use 8, 4, 2, and 1. So 8, 4, 2, and 1 here, and 8, 4, 2, and 1 here. Okay? Now, like we just did, add up whatever has 1s in it. So on this side, we're going to get 8 plus 4 is 12. And over here, we're going to get 8 plus 1, which is 9. Now, if you go back to the previous page, or one of the previous pages, page 11, where Unicode is shown, right, you'll see the number 12 in hexadecimal is represented by the letter C. So 12 becomes C. The number 9 is just the number 9. So this binary in hexadecimal is C9. Okay? So all those bits, those 8 bits, in just 2 characters. That is how you go to hexadecimal. So now, going the other way around. So, just beneath that, so we'll use the example there, right? So 1F44D. So 1F44D. So that's hexadecimal. We want to get that back to binary. So, first thing we need to do is we need to look at any letters and write out the number equivalent of that letter. So, 1 is obviously 1, so that's fine. F is 15 in hexadecimal. Now that's something you will need to learn off. You will be given that in an exam. You need to know the hexadecimal system. So F is 15, and D is 13. 13? 13. The numbers stay the same. So, now we say that instead of having letters and numbers, we just have numbers, and we just convert all them to binary individually. So, for this case, for hexadecimal, we just have 8, 4, 2, and 1. We have 1, 15, 4, 4 twice, and 13. And it's the same again. So for this one, you might see it by now, but because we just have the number 1, this will just be 0, 0, 0, 1. Okay, straightforward there. So 8 into 15, it does go. 15 minus 8 is 7. 4 into 7, yes. 7 minus 4 is 3. 2 into 3? Yes. 3 minus 2 is 1. 1 into 1? 15 is 1, 1, 1, 1. Okay. 8 into 4? No. 4 into 4? Yes. With nothing left over, so zeros. 8 into 13? Yes. 13 minus 8 is 5. 4 into 5? Yes. Leaves us with a 1. So, 0. So, 1F440D in binary. Would be this. So 1, 0, 0. I'm going to have that twice. Because we have 2 4s and 1 1 0. So that, it's terrible. Handwriting is just not on my side there for some reason. 1101. So that is hexadecimal to binary. And there's another example there on the top of the next page, E9F1D. I'll let you to go that yourself, but just in case you get stuck, I'll write up the answer. Actually, I'll write it in here. So, E9 F1D. So you can do that, you can do the process yourself, it's the very same thing. But the answer that you should get is that. Okay. So, see if you can do that yourself, see if you can get that answer by yourself. If you're having trouble, you can always go back and rewatch earlier part of the video, or you can also email me if you're really struggling. Okay. So, the last conversion then is going from decimal to hexadecimal. Sorry, going from decimal to, I'm not sure what I said, going from decimal to hexadecimal. So, 72, the number 72 in hexadecimal. So, this is a bit of a strange method, but it works very well. So, hexadecimal, right? The numbers 0 to 9 and the letters A to F, okay? That is 16 different characters, right? So, what we do is, we divide 72 by 16. So, 72 divided by 16 goes in, this is the math you're going to have to get good at, 4 times, okay? With the remainder of 8. And it's the remainder that we're concerned about here. So, then we do 4 divided by 16. Can you divide 4 by 16? You can't. So it's our remainder, 0. We got 0 remainder of 4. So, now we look at the remainders and read them from bottom to top. So 72 in hexadecimal is 48. Okay? And if you get any numbers as remainders that are greater than 9, you convert them to a letter. Simple as that. Okay? Now, where it can get a bit more complicated is when you're asked to go the other way around. You're asked to go from hexadecimal to decimal. Because that is not hard necessarily, it's just hard to do in your head. It's hard to do mentally, right? So, if I show you, right, so if we go back to the 2023 paper, we look at the very start of this class, and you look at question 2. So, 2023 question 2 says, information systems can represent numbers in decimal, binary, and hexadecimal format. Many software developers use hexadecimal numbers. Part A was explain one advantage of using hexadecimal numbers. So you can say it's very concise. You can write, or you can represent long pieces of information in just a few short bits, right? I'm not concerned about that part of the question now. What I am concerned about is part B, which says convert the hexadecimal number C9 into a decimal number. Okay, so we know what the answer should be, because we've done it already. So, there's 2 different ways you can do this, right? One I think is significantly easier. Well, sorry, there's a quick way and there's a long way. The quick way happens to be the hard way. So, first things first, we convert any letters into numbers. So we know C is 12 and 9 stays as 9. So, what you do now is, because obviously, as I said, we have 16 different values in the hexadecimal system. This being 16 to the power 1, 16 to the power 0, right? You have 16 to the power 2 and 3 and so on. So, to go from this to decimal is 12 by 16 to the power 1 plus 9 by 16 to the power 0. Okay? Now, I don't know about you, but I certainly cannot do that in my head. So, what is the answer? I'm going to have to look at the marking scheme, because as I said, I can't do that without a calculator. That is 192. Plus 16 by 0 is 1. So 9 by 1 is just 9. So that's 201. So that's the short way of doing that. Now some people might be able to do that fine, especially if your maths is very good. For those of you who think, I don't know about that. The other way you can do this is by doing it through 2 steps. Firstly, converting C9 into binary and then going to decimal. So, we have our 12 and 9, so we can just, using our 8, 4, 2, 1 system twice, we'll get it to binary first. So, 12. 8 into 12, yes, remainder of 4. 4 into 4, nothing left. For 9 then, 8 into 9, yes. 9 minus 8 is 1, so. There's our binary number, then we just do 8. Sorry, nearly made a mistake there. So now, once we have it as binary, now we switch to our ASCII system. So we're back now to 128, 64, 32, 16, doesn't quite line up, but 8, 4, 2, and 1. So now we have 128 plus 64 plus 8 plus 1. So 128 plus 64 is 192 plus 9 is 201. So either method is fine, both perfectly valid and written in the marking scheme. So there's, like, the examiner isn't going to care which method you do, it's just whichever one is easiest for you. Okay? So that's the number systems covered and all the different conversions going between them. So none of them I don't think are overly hard. There's just a lot of different versions that question can come up. But I think with a bit of practice, you can do them easily. And it should be a short question you bank on. Okay. So the last thing, the very last thing, page 15. The last thing to do with numbers, you'll be glad to hear, is adding binary numbers. So adding binary numbers is very simple because it follows 3 simple rules. 0 plus 0 is 0. 1 plus 0 is 1. And 1 plus 1 is 0. And you carry the 1. So, for example, add the binary numbers 0, 0, 1, 1. 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and 0, 1, 0, 1, 1, 0, 0, 0. So, just like addition when you're in primary school, we start over here. So 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 0, 1. 1 plus 1 is 0. And carry the 1. 1 plus 1, 0. Carry the 1. Sorry. 1. Yeah, 0, carry the 1. 1 plus 1 is 0. Carry the 1. 0 plus 1, 1. So 0 plus 0 is 0, 1 plus 0 is 1, and then 1 plus 1 is 0. And carry the 1 and continue on. Another very easy thing to do, I hope at least. So I'm just going to make sure that I'm still okay for time. Yes, I am. We're pretty much in around the hour mark exactly. So that is data types and number systems covered and all the different types of conversions that come with that chapter. So hopefully now you understand all this and you should be banking on a short question at least, maybe for one of these to come up. Very nice. So other than that, guys, thank you very much for watching and I will see you in the next session. All the best.